Hi everybody! On today's episode of The Builder Explains, we're going to be talking about what is arguably the most important invention of the 20th century, the switch.
Hey, I was watching something.
Hi everybody, and welcome to today's episode of The Builder Explains. Now today we're not necessarily talking about something we're going to build, but we're talking about something I find very interesting, and it is more than just a switch. It is, in fact, a solid-state switch, otherwise known as a transistor. Now, transistors I think are incredibly interesting, and the reason I wanted to talk about them is because I find them fun, interesting, and incredibly important to the 20th century and everything after. Because our lives straight up wouldn't be the same without them. At all. Now, why did I introduce the episode by saying a switch? Well, a transistor really is a solid-state switch. There are no moving parts, but we are changing a current from either on or off or anything in between. So, let me explain. Let's walk through the natural progression of how a switch is related to a transistor. A switch is something we turn on. I'm going to use the electrical diagram version of this, but anyhow, a switch, we use our finger. See if I can draw a hand without looking like a middle finger. Oh well, I tried. Anyhow. This is terrible. Anyhow, so we use our finger to turn on the switch, right? Now here's the next progression of things. If we want to turn that switch on repeatedly without using our finger, then we use something called a contactor or a relay. And that uses magnetics to turn that on. So now we're using a small electrical current to turn on a large electrical current, right? So first, we manipulated that large electrical current with our hands. Then we moved on and we said, you know what? I want to do that quickly and I want to do that repeatedly and I don't want to use my fingers. So let's do that with small voltages, contactor. Moving up the ladder to even further. What we do is we eliminate the mechanical motion altogether. Transistor. This one happens to be a NPN transistor. You'll learn about that later. Anyhow, transistor. We have, this would be our contacts, so like this would be the contacts coming in and going out. And then this is the small voltage manipulating that. So large voltage and small voltage. So that is the progression to which a switch that you manipulate with your finger relates to a transistor. Let's start talking about transistors themselves. So, a transistor, when it starts off with the vacuum tube, like I said, we have an anode or a cathode. We'll start with the cathode, right? We'll call that a C. Then we have an anode, and when we apply a voltage to this, we end up with electrons that flow towards the anode. So electrons come off of the cathode and they are gathered by the anode. Now, I want to manipulate that. So I'm going to add a gate of sorts. Here's what that did. Let's say our cathode was a positive displacement, so it gave off electrons, right? If we applied a ground to the grid, then it would collect those electrons and they would go down to the ground instead of to the anode. That's the idea, is we put a gate in there and we say, nope, you're not going to move. So that's how a transistor works. We basically interrupt the flow of electrons with a gate. Now, I'm saying these terms because later on they're going to matter to you quite a bit. let's talk about how transistors in the solid state form are made. In the vacuum tubes, things are actually very easy to understand because we have our poles are sticking right out in the middle of nowhere with a vacuum applied, and you can see it. It's easy to understand. At least I think so. I found it very easy to learn electronics based on vacuum tubes because it was a very visible way of learning. When you move on to solid states, it's not so visible. The silicon world is something you have to actually understand. And in order to understand the silicon world, we're going to talk about molecules. I'm going to dumb this down a good bit to understand why the whole silicon thing even works in the first place. First, we have to understand why electricity flows right from the get-go. So we're going to use the silicon molecule as an example. Now, these are not accurate numbers. If you want to know the accurate numbers, you can do what I did and Google it. But we're just using this as an example. Let's say silicon has, an atom, right? So you got protons and neutrons right there in the middle. And then let's say silicon has 2 valence shells and it has a total of 10 electrons. I'm not sure what this element is because I didn't look it up, but I'm just using this as an example. Basically, the idea is that silicon has a complete outer valence shell. That's where the electrons orbit the nucleus. When your valence shell is complete, it's considered very stable, and it's very difficult to add or knock off electrons. Because it's difficult to add or subtract electrons, it becomes a very good insulator, right? Same thing with plastics and glass. It's difficult to add or subtract electrons to those molecules. That's what makes them a good insulator. You might ask, then why are they using silicon for computer chips and transistors? Well, here's the thing that makes this work. The silicon having a very complete valence shell makes it a very good insulator. But it being a very good insulator is a positive and a negative. So here's what we do, or here's what they do, in order to make it so we can use silicon as a conductor as well. They use a process that they call doping. Don't ask me where the name comes from. It's kind of funny, but that's what they call it. So what they're going to say is they're going to say we got so many silicon molecules. These silicon molecules are very stable. They're a good insulator. Well, what I'm going to do is I'm going to mix in a good conductor, molecules that are a good conductor in the mix. I'm going to use X's for that. So the O's are good insulators, and then we dope it with good conductors. Now what this allows us to do is say we want to create a wire or a conduit in that silicon. We simply layer the doped silicon that is conductive in the middle of 2 layers of regular silicon that is an insulator. Molecules can either have extra electrons or not enough electrons. For example, copper has 1 electron in its outer shell that could take 36 electrons, I think. So basically that 1 electron is very easy to knock off. And the thing's like starving hungry for more electrons, so it's very easy to add electrons. So if we take a molecule that, say, has an extra electron, we say that has a dot. But if we have a molecule that, say, has not enough electrons, like say we have 4 electrons and we want 6, then we have a hole. All right, and the difference is one molecule wants to give off its electron, the other molecule wants to attract electrons. So knowing this, we can take 2 different kinds of elements and we can dope our silicon with those 2 different kinds of elements. Now that is an advantage for us in how we design our transistor. So let's say I create a layer of molecules or silicon molecules that are doped with other molecules that want to give off electrons. Oh, phooey, I'll just draw it like this. This layer has extra electrons. Now let's say I come down here and right next to it, I build a layer of molecules that doesn't have enough electrons. I have a layer with too many electrons and a layer with not enough electrons. Now these two layers are conductive in their own respects, but they're conductive in different ways. What happens here is that this layer right in the middle here, they kind of transition over. This one will give off an electron and this one will take it, and this one will give off and that'll take it, until there's kind of a balance built right in the middle. But that balance can only go so far, because electrical force, like these molecules, once they start giving off electrons, it can't, there's nothing to push it. Like there's nothing to fill the space in as those electrons come off. So those molecules end up wanting their electrons back eventually, and you end up with a dead space here where the molecules are kind of balanced, but it's a strained relationship. Now what I just drew for you is considered a diode. Now a diode, also this thing's also a diode. It's a heavy-duty sucker. Now a diode is a silicon-based solid-state electronic check valve. That means that it only allows electricity to flow in one direction, and I'll show you real quick here how that works. So because a diode has too many electrons on one side and not enough on the other, the electrons want to equalize. They do. They want to equalize. But we strain ourselves to the point where we just can't get this done. So here's what happens. If I apply a voltage to either end of this diode, so up here so you can see it. So if I apply a voltage to either end of this diode, if I try feeding electrons to this end, and I try taking electrons from this end, I only serve to strain this relationship right here in the middle even more. I can't feed what's already there. I can't take away from what's not there. So electricity will not flow in that direction. But follow me here. If I reverse that, and I now take away electrons from the molecules that have extra, and I give electrons to the molecules that don't, I start filling in these holes. Once I start filling in these holes, and I start taking away these, I completely relieve the pressure here. Once that pressure is relieved, and now I have a balance of electrons across the silicon, electricity can flow. Now, this also creates what we call a forward bias voltage. That means it takes so many volts, or so many electrons, to fill in the gap before it actually starts flowing. In other words, we have to push on it a little bit to get it to open. We have to fill in those gaps to get it to open. Now you might be asking yourself at this point, man, this guy's so boring. I know, this guy's boring, right? I'm getting to the point. Let me erase this real quick here. A transistor is essentially just is essentially two diodes put together, actually. Now what that means is, and this is where the doping comes in, the two different ways of doping. If I have 3 layers and I put extra molecules on this side, yes, I know, I changed up the way I'm drawing extra. And I put extra molecules on this side, extra electrons, let me be specific. So I have molecules with extra electrons on this side and extra electrons on this side, and then I have molecules with not enough electrons in the middle. Now, if I apply a voltage to either side of this circuit, I'm never going to get anywhere, no matter how I apply that voltage. Because as soon as I try feeding electrons to this side, well, they already have electrons. So I can't push any more there. And this side, I can take away the electrons until I get to the point where I'm equalized to the middle layer, at which point I'm not going to take away any more electrons. There's just no more to take. At that point, you reached a dead end. So no matter, because of this middle layer, no matter which direction you apply voltage, you're never going to get through it. This is called the field, right in here. Now how this relates to vacuum tubes, this is our gate. This right here, this layer of molecules with not enough electrons is called the gate. Well, in the solid state form, it's called the field. In the vacuum tubes, they called it the gate or grid. The reason we call it a gate in layman's terms is because we can control that. Let's say I apply a positive voltage to the middle layer. Now all of a sudden I start filling in these electrons and boom, it equalizes to one side. Now I can take away electrons and I can feed electrons and it rolls right through. We equalized it. The other side, the inverse works as well. If all right, we're going to cut and do some erasing here. So the inverse works as well. If I have a bunch of molecules that don't have enough electrons, and then I have molecules that have too many electrons in the middle in our field, now in order to get electricity to flow, I need to take away electrons. As soon as I drain the field, drain the swamp, as soon as I drain the field, now electricity can flow. Now we equalize the layers and boom, electricity flows. That is how the doping and the different ways of doping affects transistors. The never points in transistor, or NPN, that one you want to add electrons to the gate. So that has the negative in the middle. Whereas the PNP, you want to take away electrons from the gate. So you want to drain the field. It's just two different ways that we can control electronics. Here's an interesting piece of trivia. In the 1890s, New York City had an entire fleet of electric taxi cabs. Bet you didn't know that one. Now this, gentlemen, is the peak of what we're talking about. A CPU. This is my i7 8700K processor. This is what makes most modern computers do their thing. In fact, over here I have an i9 9900K. Same thing. This essentially, and I say essentially because it's far more convoluted than that, but essentially is millions, if not billions, of these. Transistor, CPU. That's why this thing is quite possibly the most influential piece invented in the 20th century. Oh, another piece of trivia. The transistor, solid-state transistor, I believe solid-state, well, the transistor as we know it was invented in 1947 in Bell Laboratories by two different scientists that I don't remember their names. So that piece of trivia. So that's it, guys. That's the story about transistors. They've come from switches to relays to vacuum tubes into figuring out how to make silicon conductive and how to do it in different ways so that we can layer those different ways, and all of a sudden we have solid state switches. And when we started to create solid state switches, now you can obviously see this switch right here is good for 46 amps. That's a lot of amperage, especially for such a small circuit. Now it's not high voltage, but it's high amperage. A contactor to do the same job is, you know, at least that size. I just dropped my marker. So we make them smaller and smaller and smaller to the point where we can fit millions of those things inside a tiny little chip like this. I say tiny because that thing is small compared to the chips I'm used to working with. So that's why I say that this thing is the most important invention in the 20th century. Without it, we wouldn't have cell phones, we wouldn't have computers, we wouldn't even have calculators. So you'd still be rolling beads around on your abacus or cranking that old school calculator gadget. I want to get one of those. They're fun. So that's this episode of The Builder Explains. Messy, boring possibly, but hopefully you guys watched till this point. And if you watched till this point, I give you mad credit for surviving that entire lecture. So I really appreciate that. And hopefully you enjoyed this at least a little bit, and hopefully you learned something, and you can walk away saying, I know how transistors work. I know that transistors use molecules of silicon that have been doped with other molecules to do different things, at least two different things, and so forth and so on. So you can walk away from this episode saying, I feel a little bit smarter. That's my goal. I enjoy these things. I really like how transistors work. It's simple and elegant at the same time. So that's why I wanted to share it with you guys. So thank you very much for watching. I really appreciate it, especially if you've stuck around this far. Go ahead and hit a thumbs up on the video if you liked it. Make sure you're subscribed and hit the bell icon so you see future videos where we actually build some stuff because, you know, Renaissance builder, right? And until the next video, guys, thank you very much. You have a good night.
Bye-bye.